So, here we have the orange feather example. You can see over here on the left we have an orange, and on the right we have a feather. Now, I'm not the best artist in the world, so this is my orange and this is my feather. What do we know about oranges and feathers? Well, we know that, importantly, that an orange and a feather have a different mass. They actually have a different mass, and depending on gravity, they're going to have a different weight. Okay, so hypothetically, let's put our business hats on and let's pretend we're business people, and we've created a product, and everybody wants this product. It's called the orange feather. Okay, everybody wants an orange feather. Now, to make an orange feather, what we do is we take one orange and one feather and we combine them in this ratio to produce the orange feather. And it has to be done in this ratio. We can't take 3 oranges and 1 feather. It needs to be 1 orange and 1 feather. So we go and we get on the phone and we say, hello, Orange Orchard, I would like one ton of oranges. And then we get on the phone to the chicken farm and we say, I would like 1 ton of feathers, please. And we have them delivered. So can anyone see what the problem is here? What's going to be the problem if we have a ton of oranges and a ton of feathers? Okay, what's going to happen is that you're going to have too many feathers, because a ton of feathers is going to be more feathers, if you counted them, than how many oranges you have. So you're going to have the wrong ratio. We need to make sure that we've got the right ratio. And this is the same in chemistry as well. If we're going to do a chemical reaction, we want to make sure that we've got the right amount of each of the reactants, okay? And we can't just take a gram of one and a gram of the other, because it's not going to be the right amount, because they've got different weights, they've got different masses, okay? Now, what would happen then if we developed our product even further, and now we had a double feather orange, and we've got now 1 orange and 2 feathers that we need to combine? This is now called a stoichiometric ratio of a 1:2 stoichiometric ratio to make our double feather orange. Now we're going to have to make sure that we order twice as many feathers as we do oranges. Okay, how do we do this? We could order them in dozens, couldn't we? We could say, well, I'll have a dozen oranges and 2 dozen feathers. Then you know you're going to have the right amount. You need to order in a number, not in a weight amount, okay? And this is why in chemistry we use something called the mole. Now, we know a dozen is 12. Okay, a dozen's just a number, it's 12, right? Is a dozen 12 oranges? No, it's not always 12 oranges. It's not always 12 eggs. It's not always 12 bread rolls. It's just 12. It doesn't have any units. And the same thing is with a mole. Okay, a mole is very much the same. A mole doesn't have units. A mole isn't always a mole of carbon. It's not always a mole of hydrogen. It can be, you can have a mole of anything. You have a mole of oranges if you want. You have a mole of anything. Have a mole of oranges, have a mole of feathers. A mole is a number as well. It's not 12, but it's a number. A mole is in fact 6.02 by 10 to the 23. This is also known as Avogadro's number. And this is a mole. And that's the orange feather example. Okay, so a mole is just a number. It's a number, just as a dozen, and thus is dimensionless. You can think of Avogadro's number as the chemist's dozen, if you like. The mole is defined as 6.02 by 10 to the 23. Anything, it can be molecules if you like. 6.02 by 10 to the 23 molecules. It's just a mole, 6.02 by 10 to the 23. It's just a bit like a dozen, it's just a different number. Okay, it's almost a trillion. It's a big number. Okay, if you were given 1 mole of dollars, Australian dollars at birth, and spent $1 billion a second for your entire life, by age 70, you would have spent 0.001% of your Australian dollars that you were given at birth. Okay, $1 billion a second. If you counted every grain of sand in every ocean, on every beach, you might come close to 1 mole. Its practical use is limited to counting tiny things. So you're not going to use it to count oranges, because oranges are too big. There'd be too many oranges. So you're going to count tiny things like atoms, molecules. You could count formula units, if you like, for ionic compounds. Electrons. You could count photons. This is where it's useful. Okay, we need this huge number for counting tiny things. Okay. Avogadro lived in the early 19th century. He was an Italian savant known for his role in many different scientific disciplines. His most famous statement is known as Avogadro's law, and is a hypothesis that states equal volumes of ideal or perfect gases at the same temperature and pressure contain the same number of particles or molecules. Now this is very interesting, and this means that it doesn't matter what the gas is, could be methane or hydrogen gas or helium, any kind of gas you can name, carbon dioxide, a mole of gas will actually take up the same volume at the same temperature and pressure regardless of what gas it is. And this actually turned out to be true. It's a very interesting observation that Avogadro made. Okay. Mole, this is one kind of mole, the mole that burrows, but spelt the same way. The mole is the SI measure of quantity of a chemical entity, which can be an atom, a molecule, a formula unit, an electron, or a photon. The mole is the amount of a substance of a system which contains as many elementary entities as there are in atoms in a 0.012 kilogram amount of carbon-12. So 0.012 kilos of carbon-12. Here's some important triangles. If you always remember that your units of atomic mass are grams per mole, okay, that's also your units for molecular weight, grams per mole. If you just remember your units, you won't have to remember any of these triangles. But just in case you find these useful, okay, if you were to say divide mass by molecular weight, that would give you moles. So mass on molar mass gives you moles, okay, for example. What happens if you multiply moles by molecular weight? Well, then you get mass. This is how these triangles work. Here's some SI units. You can see that the SI unit mole is used for the amount of substance. Determining the number of moles, where a number of objects or particles are involved. How many mole of molecules are there in 3.01 by 10 to the 23 molecules of a particular substance? So how many moles are there? We know that 1 mole is 6.02 by 10 to the 23. This is 3.01 by 10 to the 23. That looks like half a mole to me, but let's just check. Is it half a mole? Looks like half a mole. So number of molecules divided by 6.02 by 10 to the 23. So we've got, okay, we have 3.01 by 10 to the 23 of them. We know that 1 mole is 6.02 by 10 to the 23. If we wanted to work out how many dozen, we'd divide by 12. We don't want to know how many dozen. We want to know how many moles there are. So we're dividing by 6.02 by 10 to the 23, and we have 0.5 moles. Easy peasy. If you want to work out how many dozen you have, divide by 12. If you want to work out how many moles you have, divide by 6.02 by 10 to the 23. Where mass or weight is involved, how many moles are there in 72 grams of water? Oh, okay. Of H2O, when hydrogen has a molar mass of 1 gram per mole, oxygen is 16 grams per mole, so H2O obviously is going to be 18 grams per mole. We need to add those together, so 18 grams per mole. Right, let's have a think about this. Mole equals the mass given, so 72 grams divided by our molar mass, which should be divided by 18. Okay, we've actually worked out the 18 on the bottom line here. 2 times 1, 2 hydrogens, 1 oxygen. Oxygen weighs 16 grams per mole. You can check these values on the periodic table. 72 divided by 18 gives us 4 moles of water. We have 4 moles of water. How much did that weigh? Weighed 72 grams. Concept checked. A sample of 26.98 grams of aluminium has the same number of moles as how many grams of gold? Well, let's work this one out. So aluminium has a molar mass of 26.98 grams per mole. So if we've got 26.98 grams of aluminium, 26.98 divided by 26.98 equals 1 mole. We've got 1 mole of aluminium. So, okay, how much would that weigh if it were gold instead of aluminium? Well, gold has a molar mass of 196.97. Well, we'll round it off to 197. So molar mass of gold, 197 grams per mole. 1 mole of gold would weigh 197 grams. Here's another exercise. Rank the following according to the number of moles, greatest to least. Okay, 107.9 grams of silver, 70 grams of zinc, 21 grams of magnesium. Well, what we need to do is use the periodic table to work out how many grams per mole each of these contain. So silver, Ag, is the chemical symbol for silver. Ag, 107.87 grams per mole. Let's round that off to 107.9. So it looks like we've got a mole of silver. Wonder what the mass of zinc is. Let's just look this one up. Zinc is 65.39. Okay, so we've got less than a mole. Will we have less than a mole? No, we've got more than a mole of zinc. So we've got 1 mole of silver. We've got slightly more than 1 mole of zinc. What about magnesium? So magnesium has a molar mass of 24.3, but we've only got 21 grams, so we've got less than a mole of magnesium. So we've got the least would be magnesium, the most would be our zinc, and silver would be in between. So if we rank these, greatest to least, we've got the greatest amount of zinc, because zinc would be more than a mole. We've got a medium amount of silver, silver's in the middle, and we've got the least amount of magnesium. We've got less than a mole of magnesium. So determining the number of moles from the number of particles, objects, molecules, atoms, or things, how many moles are there in 12.04 by 10 to the 23 hydrogen ions? So, okay, that number looks very round to me. Why does it look round? Because remember, Avogadro's number, 6.02 by 10 to the 23. This is 12.04. Looks like double Avogadro's number, so it's going to be 2 moles. So 12.04 by 10 to the 23 divided by 6.02 by 10 to the 23 gives us 2 moles. If we wanted to know how many dozen there are, we'd divide by 12. We don't want to know how many dozen. We want to know how many moles there are, so we're dividing by 6.02 by 10 to the 23. Stoichiometry. I mentioned this earlier. Okay, stoichiometry is the process of using a balanced chemical equation to determine the relative masses of reactants and products involved in a reaction. So what this equation tells us is that one H2 molecule and one I2 molecule react to give 2 HI molecules. Okay, 1 mole of H2, 1 mole of I2 reacts to give 2 moles of HI molecules. That's what this is really telling us. It's a 1:1:2 stoichiometric ratio. Phosphorus trifluoride can be prepared from phosphorus and fluorine according to the following reaction. So P4 plus 6F2 gives us 4PF3. And this is where people can get confused. How many things do we have on the left-hand side? We've got P4, which is one thing. We've got 6 F2s. Okay, that's another 6 things. So we've got 7 things, 7 objects in total, 7 particles in total on the left-hand side. But we've got 4 things on the right-hand side. How does 7 things become 4 things? This goes back to the baking a cake example. It's not anything to be confused about. We're not creating or destroying matter. Sometimes you just take more objects to make less objects. It happens. Okay? So, assuming that sufficient fluorine is present, what mass of phosphorus trifluoride can be produced from 1.55 grams of phosphorus? Now this is a little bit more of an advanced example. This is where it starts to get exciting. So if we've got 1.55 grams of phosphorus, phosphorus weighs 31, fluorine weighs 19. So when they say phosphorus, they really mean P4, okay? So first we write out the equation. There's our equation. We're retranscribing the equation. Write down the mole relationships. 1 is to 6 is to 4. This is our stoichiometric ratio. 1 is to 6 is to 4. 1 of these and 6 of those will give you 4 of these. Convert mass of phosphorus into moles. So we've got our mass given to us, 1.55 grams divided by the molar mass. Now the molar mass, and this is the trick, 4 times 31. Why is it 4 times 31? Because we need the molar mass of this molecule. One molecule, one phosphorus molecule, okay, is going to be containing 4 phosphorus atoms. So 4 times 31, 1.55 divided by 4 times 31 gives us 0.0125 of a mole, a fraction of a mole, 0.0125 of a mole. Okay, that's how many moles of phosphorus we have. We know this is a 1 is to 6 is to 4 ratio, and the ratios have to be molar ratios. They can't be mass ratios, they can't be weight ratios. It won't make any sense. We need these to be a number ratio. So we need to use a number, and we're going to use moles to represent this. So what we're going to do, and we're going to say that since 1 mole of phosphorus would require 4 moles of PF3, that would be being produced. So 4 moles of PF3 would be produced. Then how many moles of PF3 can we make from 0.125 of a mole of phosphorus? Well, we can make 0.05 moles of PF3. We can make 4 times the amount. Okay, so if we've got 0.0125 moles of phosphorus, we can make 0.05 moles of PF3. That's 4 times the amount. Multiply by 4. 1 is to 4 ratio between our phosphorus and our PF3. So as long as there's sufficient fluorine available, and we were told there is in the question, then we will produce 0.05 moles of PF3. Answering the question. Have we answered the question? The question says what mass of phosphorus trifluoride can be produced. That's how many moles. Moles aren't mass, moles are a number. So we know that there's 0.05 moles of PF3 being produced. We need to convert this into grams. So we know that moles equal mass on molar mass. 0.05 equals the mass on the molar mass, which is 88. PF3, add up the different atomic weights, you'll get 88. You can try this out. Mass on 88. So multiply that by 88. 0.05 times 88 will give you the mass produced, which is 4.4 grams. 4.4 grams of phosphorus trifluoride. Percent yield. This is an important indicator of the efficiency of a particular lab or industrial reaction. So on that previous example, we decided that, yeah, we could make 4.4 grams of our product, theoretically, on paper. But what happens if you go in the lab and you do the experiment and you pull out the balance and you weigh how much you've produced? Hang on a minute, we don't have 4.4 grams, we've only got 4.0 grams. So we've got less than was on paper. We can say we've got a percentage yield. So you take your 4 grams, you divide that by 4.4 hypothetically, and you'd get a 91% yield, roughly. Okay? A theoretical yield is the maximum amount of a given product that can be formed when the limiting reactant is completely consumed. This is on paper. This is theoretical yield. Our percent yield is the actual yield. Okay? Well, it's not the actual yield, it's a ratio of the actual yield to the theoretical yield. So the actual yield is how much you've physically got when you perform the experiment in a lab and weigh how much you've made. So percent yield is expressed as a percentage. Take your actual yield, divide that by your theoretical yield, multiply by 100%, you've got your percent yield.